Today I will say obviously some question of linear algebra. Actually, today's goal of this lecture is I will say some linear transformation. Then I will say one question about Jordan block. Okay? Let's see the question at first. First question. Which had come CSIR Net Math September 2022 exam? The question is AB n cross n matrix with entries in the real field such that A and A square have the same rank. Then consider the linear transformation T from Rn to Rn defined by TV equal to AV where for all B belongs to Rn. Then which of the following statements are correct? Option 1. Kernels of T and T composition T are same. Option 2. Kernels of T and T composition T are equal dimension. Option 3. A must be invertible. And option 4. Identity plus A must be invertible. Here AB linear transformation from Rn to Rn because here given AB n cross n matrix with real field and the mapping is such type TV equal to AV, that means the mapping is such type, and here since notice A and A square have same rank. Since A and A square have the same rank, then obviously rank of T cube contain rank of T square. And rank of T square contain rank of T cube. We all of us know this property, this type of property. Similarly, rank of T to the power 4 contain rank of T cube, this type. We all of us know this property. And always kernel be opposite always. Here when rank would be increased, this relation rank of T to the power n actually contain rank of T to the power n minus 1. Okay. Kernel always contain kernel T square, kernel T cube, so on, because if x belongs to kernel T, then obviously Tx equal to 0. Now multiply this equation by T, then this would be T square x equal to 0. And from this relation we can tell x belongs to kernel T square. So obviously kernel T contain kernel T square. Are you getting? Well. Similarly, we can tell kernel T contain kernel T square and kernel T square contain kernel T cube, so on. And rank would be just different. Actually rank contain always lower part of the rank T to the power n always contain rank T to the power n minus 1. I hope my all viewers know this part because I have discussed this part in my previous video. Here also in the question has given rank of A and rank of A square has same rank. Here given rank of A equal to rank of A square. So by rank nullity theorem we can tell rank of A plus nullity of A equal to n. Similarly, rank of A square plus nullity of A square would be n because rank of A equal to rank of A square. And since AB linear transformation from Rn to Rn, so obviously A square would be linear transformation from Rn to Rn. And since rank of A equal to rank of A square, that means obviously nullity of A equal to nullity of A square. And by this relation, since kernel T contain kernel T square, and here since the linear transformation denoted as A, so kernel A contain kernel A square. Okay? Have you understood? And since here kernel A contain kernel A square, but their dimension is same because nullity of A equal to nullity of A square. When a subspace contain one another, but their dimension same, that means obviously this space or these two subspace are equal. That means kernel of A equal to kernel of A square. And this is equal because the dimension is same. Okay. So, let's see the option. Here, option 1 has indicate kernel of T and T compose T has same. Obviously, this is same because I have got kernel of A equal to kernel of A square. And notice option 2, here given kernel of T and T compose T are the equal dimension. This is obviously same because I have got nullity of A equal to nullity of A square because rank of A equal to rank of A square. Option 2 also right option. And option 3 imply A must be invertible. Consider A equal to 2 cross 2 0 matrix. And notice here rank of A equal to rank of A square. All condition has satisfied. But A does not be invertible here. So option 3 is a wrong option. And option 4 indicate In plus A must be invertible. Where? Obviously In be n cross n identity matrix. For this, consider A equal to this matrix. Then rank of A equal to 3 and rank of A square equal to 3. And here this is satisfied OR relation, rank of A equal to rank of A square. But identity plus A equal to here 202, which is actually not be invertible. So, option 4 also right option. Sorry, wrong option because here I have got identity plus A not be invertible. Have you understood? I hope my all viewers have understood. This is actually property, some basic property. This question depends on some basic property. Okay. Now I will see one question which had come December 2015 exam. The question is AB n cross n matrix over the complex number such that every non-zero vector of Cn is an eigenvector of this matrix. Then option 1, all eigenvalues of A are equal. Option 2, all eigenvalues of A are distinct. Option 3, A equal to lambda I, where for some lambda belongs to complex number and I is an n cross n identity matrix. Option 4 indicate if chi A and Ma denote the characteristic polynomial and minimal polynomial, then that imply chi A equal to Ma. That means that imply characteristic polynomial of this matrix equal to minimal polynomial of this matrix. Here, every non-zero vector of Cn is an eigenvector of the matrix A. For this, for lambda belongs to complex number, since here v1, v2, vn be all be eigenvector, then by definition obviously A Vj equal to lambda Vj, where j equal to 1 to up to n, and here this Vi is nothing but this is all eigenvector. Then that imply A Vj minus lambda Vj equal to 0 vector. That imply A minus lambda I times Vj equal to 0 vector. This is the definition we all of us know. Since here this vector is actually eigenvector, so obviously this is the basis vector of complex number C, because here Cn over the field C. So every linear combination can be written as this Vj. Therefore, for alpha j belongs to complex number, we can write this as alpha j times A minus lambda I Vj equal to 0. Okay? And this is we can write as actually summation j equal to 1 to n A minus lambda I times alpha j Vj equal to 0. And obviously this is nothing but this is basic scalar. So just omit this part from summation. Then this would be A minus lambda I times j equal to 1 to n alpha j vj equal to 0 operator, and this means a minus lambda I equal to times v equal to 0, where v belongs to all vector in CL. Okay, so that imply obviously a minus lambda I equal to 0 since v with the non-zero eigenvector, and that imply since a minus lambda I equal to 0, that imply a equal to lambda I. That means a equal to lambda I, and this matrix is nothing but this is actually the scalar matrix. Okay, therefore here all eigenvalue of this matrix are equal because here the scalar matrix. Now let's see the option. At first, option 3, a equal to lambda I, where for some lambda belongs to complex number and I is an n cross n identity matrix. This is obviously right option. That means option 3 is the right option. And notice option 1, all eigenvalue of a are equal. Since this is the scalar matrix, so obviously option 1 is the right option. And option 2 is a wrong option. All eigenvalues of a are distinct. This is wrong option. And notice option 4 is option 4. If chi a and ma denote the characteristic polynomial and minimal polynomial of this matrix, then chi a equal to minimal ma. Is this option is true? Since the matrix is scalar matrix a equal to lambda I, that means obviously the minimal polynomial is such types x minus lambda, and the characteristic polynomial would be such type x minus lambda to the power n, where n belongs to natural number. That means option 4 also wrong option. Only option 1 and option 3 are right option. Have you understood this question? Oh well. Now I will see one question which had come CSIR NET 2019 exam. This question is basic question and this question is part B question. The question is PAX, which denote the characteristic polynomial of a matrix. Then which of the following matrices is constant? Here PAX minus PA inverse x. Option 1 3324, option 2 4322 23, option 3 3243 and option 4 2334. Which of the following matrices be constant? Okay, here PAX minus PA inverse x is equal to constant given. We all of us know characteristic polynomial is such type. Obviously, characteristic polynomial of a is x square minus trace of ax plus determinant of a. Since here 2 cross 2 matrix, so obviously characteristic polynomial would be such type. And PA inverse would be x square plus trace of a inverse x plus minus det of a inverse, which is equal to c, means obviously constant. That means just omit this part. Then this would be trace of a inverse minus trace of a times x plus det of a minus det of a inverse equal to constant. This is equal to constant, so obviously this part would be 0. So trace of a inverse minus trace of a equal to 0, and since trace of a inverse minus trace of a equal to 0, then that imply obviously trace of a inverse equal to trace of a. Okay, that means we have to find which matrix has satisfied this property, trace of a inverse equal to trace of a. For this, at first consider one arbitrary matrix whose entries are a, b, c, d. Then trace of a would be a plus d, and a inverse equal to actually, obviously this equal to actually adjoint of a divided by determinant of a, and this is equal to actually adjoint a means dA, and here minus b minus c, and determinant of A means AD minus BC. So, trace of A inverse equal to actually A plus D over AD minus BC. So, since trace of A equal to trace of A inverse, that means obviously this determinant AD minus BC would be 1. Okay, that means following this matrices we have to show which matrix will satisfy AD minus BC equal to 1. Have you understood? This is very conceptual. Notice here determinant is 3, here 6, here 1 and here minus 1. So, only option 3 is the right option. Okay? Oh well. Now I will discuss our next goal. I will discuss one example of Jordan block. And this question had come CSIR net 16 September exam. The question is, W be the C-linear combination of the following function, where f1z equal to sin z, f2z equal to cos z, f3z equal to sin 2z and f4z equal to cos z. Consider T be linear operator on the subspace W who is given by complex differentiation. Then which of the following statements are correct? Option 1, dimension of W is 3. Option 2, span of F1 and F2 is the Jordan block of this linear transformation T. Option 3, T has 2 Jordan block. And option 4, T has 4 Jordan block. T be the linear operator from W to W, where W is the span of sin z, cos z, sin 2z, cos 2z. Okay? W is the span of this function, and we all of us know these four functions are linearly independent. So, dimension of W is 4. Have you understood? Okay. Now let's see the question. Here first option has given dimension of W is 3. This is wrong option. And option 2 imply the span of F1 and F2, where F1 is the sin z and F2 is the cos z, is a Jordan block of this linear transformation T. And option 3, T has 2 Jordan block. And option 4 implies T has 4 Jordan block. Here F1 is sin z, F2 cos z, F3 sin 2z and F4 cos 2z. Consider F1 corresponds 1 0 0, F2 corresponds 0 1 0 0, F3 corresponds 0 0 1 0 and F4 corresponds this function 0 0 0 1. Okay? Since T be linear operator on W given by complex differentiation. Okay? That means since I have considered F1 is 1 0 0 and since this operator is complex differentiation, so since I have considered this function as a correspond to this basis, so since this is complex differentiation, so sin z corresponds to cos z, okay, and cos z means F2 which is actually 0 1 0 0, cos z corresponds to minus sin z, and this is actually corresponds to this basis 1 0 0 minus 1 0 0 0. Then sin 2z corresponds to 2 cos 2z and cos 2z means F4. That means this would be 0 0 0, 2, and F4 means cos 2z. Cos 2z, since this is complex differential, this would be 2 sin 2z, and sin 2z represent F3. That means this is actually 0, 0, 2, 0. Matrix representation with respect to this basis would be 0, 1, 0, 0, minus 1, 0, 0, 0, 0, 0, 0, 2, here 0, 0, 2, 0. Okay, and notice here one block and here another block. Have you understood? And now notice the option. First option has indicate span of F1 and F2 is a Jordan block of T. For this, like the Jordan block would be, here eigenvalue is plus minus I, and here minus 2, because here cos 2z equal to minus 2 sin z, so here minus 2. So for this, here eigenvalue is plus minus I, and here eigenvalue would be plus minus 2i. So Jordan block would be such type: I 0, 0, 0 minus I 0, 0, 0, 0, 2i 0, 0, 0 minus 2i. Have you understood this Jordan block? And notice here 4 Jordan block of one order. Okay. Span of F1, F2 means span of sin z and cos z. Obviously, this is this column 1, 0, I 0, 0 and 0 minus I 0, 0. And this is actually the Jordan block. So, option 2 is the right option. The span of F1 and F2 is a Jordan block of T. And option 3 has indicate T has 2 Jordan block. This is obviously wrong option. And option 4 also right option, T has 4 Jordan block. Notice here there exists 4 Jordan block of order 1. Okay. This is our option. Have you understood this question clearly? Okay. Oh.